Assalamu alaikum wa rahmatullah. Today I'm going to review with you chapter 9 from a very excellent book everybody familiar with, Contemporary Orthodontics by William Proffit, the 6th edition. And this is part of our book review that we do for the Saudi Board in Orthodontics. As you can see, the chapter title is Mechanical Principles in Orthodontic Force Control. It consists of 4 parts. The first one about the elastic materials and the production and how we can produce orthodontic forces, like the physical properties or basic properties of wires in specific, and then design factors in orthodontic appliances, mechanical aspects of anchorage control, and finally determinate versus indeterminate force systems. And I'm going to do it in maybe 3 or 4 parts. As you know, one of our objectives always is to produce light continuous force by orthodontic appliance. And the challenge in designing and using any orthodontic appliance is that we can produce force systems that fulfill these criteria. Produce light continuous force. Not too much force, not too less. So to do that, we have to design our force system and use materials or wires that have these features or certain features that help us to deliver this type of force. The main objective of our of this concept is to produce predictable outcome every time and then with every patient. So we have to consider, to do that, both elastic materials and mechanical factors in response of the teeth when we design our orthodontic appliance. The elastic behavior of any material always is defined in terms of stress-strain response to an external load. So when we want to study elastic behavior of wires, for example, we have to study it on what we call stress-strain curve or load deflection curve. What is stress? Stress is the internal distribution of the load, defined as force per unit area. So what happens in the wire as a result of the force. Strain on the other hand is the internal distortion produced by the load, defined as deflection per unit length. So when we study orthodontic arch wires or springs, we study them in these 2 models, either cantilever or supported beams. This is the cantilever model, and this is the supported beams. Of course, this one, an example for this one, is when we use springs like canine extrusion spring, or when we use intrusion arches. And this is supported beam, like when you have two wire in between 2 brackets. Force deflection curve, and you can see that when you want to study the elastic properties of any wire, for example, you want to apply force. Let me use the laser. You want to apply force and see how much deflection you have and how the wire will react relative to this force. And the internal, we can develop or generate another curve, which we call a stress-strain curve. So instead of having force, we'll have stress. Instead of having deflection, we have strain. Again, the stress-strain are the internal features of the material, while the force and deflection, the external features. So how can we calculate the internal stress-strain? Can be calculated by considering the cross-sectional area and the length of the beam, which is here the wire, for example, And if you look at this curve, force deflection, we have several definitions that we should know. First of all, the stiffness. Stiffness represents the slope of the linear portion of the curve here, which is force over deflection. As you can see here, the stiffness is given by the slope of the linear portion of the curve. The range is the distance along the x-axis to the point at which permanent deformation occurs. Any permanent deformation occurs, yani before the yield point. So how much the wire can bend elastically and then go back to its original form without deflection. This is range. The yield point is the point at which point 1 permanent deformation has occurred. So we will have point 1 permanent deformation in the beam. Also clinically, when we say spring back, this is a very important feature, that the wire can stay, the wire can be deflected and can be used after the yield point, where we don't have any more like which we don't expect the wire to go back to its original shape. And then this is the point of arbitrary clinical loading. This is where the wire can be used even after bending it permanently, so in the plastic limit. And this is failure point where the wire breaks. So these are the different definitions that we should know. Here, as you can see, this is the stress strain curve, which is equivalent to the load deflection curve that I described earlier, but it represents the internal features of the beam or the material being studied. And here the book is introducing 3 important points: ultimate tensile strength, yield strength, and proportional limits, and all represents in somewhat different way the maximum load that the material can resist and represents the strength of the wire or the beam. The first 2 points, the proportional yield strength, are very similar. That represents the point at which permanent deformation is first observed. And you can see this linear relationship is known as Hooke's law. And it also introduced the definition of stiffness and springiness. You can see the stiffness of the wire is inversely proportional to the E, which represents the modulus of elasticity of the wire. And springiness is inversely proportional to the modulus of elasticity of the wire. So precisely determining the proportional limit, which I described before, is very difficult. That's why instead a more practical indicator used is the yield strength, which you can define by drawing the intersection of stress-strain curve with a parallel line offset at 0.1 permanent strain. So the point at which 0.1% permanent deformation occurs is defined as yield strength. So typically, the true elastic limit is not proportional limit and not yield strength. It's between these 2 points. But both serves as good clinical estimates of how much force or deflection a wire can withstand before permanent deformation occurs. A third point, which is the ultimate tensile strength, is the maximum load the wire can sustain. It's of course reached after some permanent deformation at greater than yield strength. So it represents the maximum force that the wire can deliver if used as spring. So it is also important clinically because it is different between stainless steel wires and titanium alloy wires. These are the 3 important points that were described here. of nickel titanium alloys, which are the NiTi wires, was a breakthrough in orthodontics. Why? Because after that, we stopped doing a lot of wire bending that we used to do when we used the edgewise appliance, where we had to do a lot of loops and steps and wire bending between the brackets to increase the springiness and the flexibility between the brackets by the concept of increasing the arch length will increase the flexibility or springiness of the wire. So then a lot of companies introduce several NiTi wires, which we call nowadays nitinol, like orthenol and others, and we had a lot of improvement in the NiTi family of wires. Important properties of nickel titanium alloys is the poor formability, it's non-bendable wire, and at the same time high springiness of the wire. So if we look at the curve of nickel titanium alloys, you'll find it more horizontal, as I mentioned earlier, than the stainless steel wire. So as I said, if we have more horizontal slope or curve, we expect the wire to be less stiff and more springy. But in order for us to understand the rest of the properties, it's very interesting wire. And we should know that this NiTi wire can exist in more than one crystal structure at intraoral temperature. So it can change from one stage to another, from one crystal structure that has certain properties to another one. So for example, at high temperature and low stress, it can exist in simple cubic structure called austenite, and at low temperature and high stress, it can be stabilized in monoclinical phase called martensite. Although this is a feature of many other alloys, it's unique here because the temperature change can occur at intraoral temperature, like around 37 degrees or around it. This unique feature of NiTi give the NiTi wire two remarkable properties: that it can be heat activated, and describing it as super elastic wire. Heat activation properties refers to the ability of the material to go from a martensitic state to an austenitic state when the temperature is increased, like from room temperature to mouth temperature. This feature is called thermoelasticity. Was very important to the original NiTi used in the space program, but was difficult to use in the original orthodontic wires. Still, these wires are important in many ways, not only the heat or thermoelasticity features. They have so many other important features that we're going to discuss. Of the thermoelasticity feature of these wires, they have another important property, which is shape memory. So which refers to the ability of the wire to go back to its original shape after being plastically deformed while in the martensitic form. So let's explain this example. When you set the wire at an elevated temperature above that transition temperature between the martensite to austenite, then you cool down the alloy below the transition temperature, then it can be plastically deformed in the martensitic stage. But the minute you raise the temperature again, the original shape will be restored. In other words, when it is heated enough to regain austenitic structure. So this is exactly what we do. The wires are manufactured sometimes as spaghetti, like at room temperature. You can find them as in the martensitic stage. At low temperature, you can find them soft wires. So this will allows you to fit the wire any cross section of wire, like even thick wires, you can fit them in while they are soft. So when the temperature increases to mouth temperature, which is 37, the wire will try to restore its original shape and go back to the austenitic stage or state. Feature of the nickel titanium alloys, beside the shape memory and the heat activation, is the superelasticity, which refers to large reversible strains that certain wires, certain types of niti wires, can withstand due to the martensite austenite phase transition. This reversible deformation can be over 10 times greater than similar dimension arch wires in other materials. So superelasticity means that when the wire undergoes stress, or it transform or change from one phase to another, not due to temperature change, but due to stress application. In engineering, they call this feature pseudo elasticity, and owing to the idea that non-linear stress strain curve that they have, which is not similar behavior to the linear stress strain curve that we see, for example, in the stainless steel wires, that relationship of Hooke's law that we talked about before. So materials that have this superelasticity are austenitic alloys that undergo transition to martensite in response to stress. So when you apply stress, it will move from austenite to martensite phase. So the stress is a mechanical analog to the thermally induced shape memory effect. This is because the temperature usually in those wires is temperature change or transition temperature is very close to room temperature. The difference is here those wires that have the superelastic materials or superelasticity property is due to the fact that those wires deform not by stretching interatomic bonds that occurs in the stainless steel wires and other wires. Here it's a little bit different, that the deformation is reversible and it occurs in the internal structures after a certain amount of deformation. This diagram shows the bending moment deflection curves of stainless steel versus regular niti, which is the M niti, the original one, and the A niti, the austenite, that has superelasticity property. You can see that with general all niti wires, they have more horizontal slope curve than the stainless steel wire, which means that they are more flexible. So after initial level of force, you can see that these wires start to bend and they develop flat almost. The A nitile develops almost a flat curve that has a plateau, and which means that upon different degrees of deflection, 20, 40, 60, or even more, the amount of force delivered or the moment developed by these wires will be the same, which is a unique feature of this superelasticity of these wires. This is what I explained in the first slide, the previous slide, that this transformation manifests in the most flat section of the load deflection curve, which means that the initial wire can exert about the same force whether it was deflected a relatively small or large distance, which is a unique and extremely desirable characteristic of these A-niti wires due to their superelasticity features. Stress strain curve illustrates or show us the transition, which is very easy transition between the austenite phase to the martensite phase. So this represents the austenite phase. After applying certain amount of force, the wire will continue elastic until it reaches certain stress level that will start the transition from the austenite phase into the martensite phase. And this stress strain curve represents, or it represents, or it shows the curve of the austenite or A-niti wires. You can say start by the A phase until it reaches certain level of force. When we apply certain level of force, the wire to deform into the M martensite phase and complete it at the C phase. After that, after the C, at the C point, the transformation into the martensite is completed, and the martensite structure start to deform elastically up to point D. But our wire, they never reach point D. But if we continue explaining the wire, we can see that at point D, this is the yield strength of the wire at which or after which the wire will start to plastically deform. And if it reaches to this point, it might reach to the failure point later on here. But another important feature that I would like to talk about is for these wires, the A-niti and superelastic wires in general, they have the loading curve and unloading curve. In other words, that the amount or the level of force that you need to load this wire on the brackets is higher or different than the force or the load that is delivered by the wire on the bracket, which we call the unloading curve. Slide, you can see that the unloading curve start again from C1 here, because we said we never reach to D, and then it goes down to F. As the teeth moves, the unloading curve will go to F point, which indicates the maximum stress on which the stress-induced martensitic structure on unloading can exist. So this is again equivalent to C, the maximum unloading stress for the martensitic phase. And then it will be reduced until it goes to G point, where the austenitic structure is completely restored, and we start to see the austenitic phase. And then it go down until it reaches to the zero level. And you can see here an important feature that is there is a small portion of total energy loss here that is irreversible during during the transition from loading to unloading, which I mentioned, and we called it hysteresis. To summarize again, that we have two important properties of the nickel titanium alloys, especially the A-niti: shape memory and superelasticity. Shape memory, which is thermal or heat activated. Superelasticity is stress activated, which is mechanical one. And here it shows that these two features, the shape memory and superelasticity, are inherently linked together, and he gave two examples here. For example, superelastic materials must exhibit a reversible phase change at a temperature that is lower than the mouth temperature for the austenite phase to exist. And on the other hand, the shape memory alloys, which are the heat activated, should have, in order for them to have exceptional range clinically, they should have stress induced transformation. So these are the two examples, and you can see that this feature was expressed in the A-niti, and because of this close interaction and close relationship between the two, wire displacing martensite austenite transition, whether they are superelastic or heat activated, are subsequently referred to as A-niti. So A-niti include both superelastic wires that can respond to stress, and the heat-activated wires that respond to heat. All other nitides other than the A nitides are called M nitide. They are because they are stabilized in the martensitic form. This is the original nitide that we had, without undergoing this intraoral phase transformation. And this was the original nitide because at that time they couldn't express this transition from one phase to another. If we look at the history of nitide wires, the original nitide was the M nitide, which was first introduced by Unitec, and the name was M nitide or nitinol wire, nitinol, which was exceptionally springy and quite strong, but has poor formability. When we say formability here, that it does not allow the transition from one phase to another. In the late 1980s, we started to see the austenite grain structure, the A nitide, which was, as I said, the superelastic ones. These wires exhibit superelasticity and or shape memory in various degrees. Superelasticity, and it can be the transition from one phase to another can be induced by stress and can respond to heat at the same time. The author here is trying to warn us not to believe 100% that these superelastic wires are really superelastic, because we don't have enough laboratory data for to believe that. So at this point of time, he is asking us to be careful in choosing our wires. An important feature of the A-nitide wires is that the unloading curve, you see the diagram here, this is the bending moment or force deflection curve. You can see that this is the loading curve and the green one is unloading. So the unloading curve is different than the unloading curve. The loading is different than the unloading. So what I mean that when we need, this is the amount of force that we need to load to put the wire on the brackets, but the green one is the force delivered by the wire on the brackets. So when it's trying to unload. So if you activate the wire up to 80 here, you can see that the amount needed to load the bracket, to load the wire on the bracket, was more than 1000 gram millimeter the moment. And then with time, the loading quickly decrease and become less and less and less until it go back to 0. And you can see the difference. This is the difference that I mentioned before, which they call hysteresis, energy loss that we have, which is unknown why it happens. So this means that the force that it delivers, the A-nitide, is not the same as the force applied to activate it. Here, this is an important feature. We can use it clinically to activate wire. So instead of changing wire every time and then, you can reactivate the wire by just untying the same wire and retying it. So because we know when we had 80 degrees of deflection, yani high displacement of the tooth, we had this amount of force, and it decreases until the next visit. This is the next visit. So the deflection decreased from 80 to 40. So if we, at this stage, if we remove the wire and retie it, we can increase the unloading force and reactivate the wire. So this is an important thing we can use to activate the same wire instead of changing wire from one to another. It is known that bending A-nitide wire is difficult unless you remarkably bend it beyond its plastic limit. But the feature of heat activation of these wires was used to bend wire. How? By passing an electrical current between electrodes attached to the wire or a segment of it. So this was used by Miura et al., who introduced a Japanese super elastic wire, where they align the teeth on the cast, and then they design their post-treatment occlusion that they want, bond brackets on it, and then they force night-eye wire, a night-eye wire, into the brackets, and then heat treatment it. So it memorized its shape, and then they use it intraorally. The idea was that they wanted to use it to treat like the whole case. One arch can treat the whole case, which also incorporates finishing bends. So theoretically, this can be done, but and they saw the Japanese guys use a certain machine to heat treat wires and use them to treat cases. But nowadays, currently, this technique is used only for computer-assisted fabrication of the initial wires only for lingual orthodontics and not the whole treatment, just the initial wires. Properties of A-night tie made it the preferable or the preferred material for initial arch wires and coil springs fabrication, in which you need a long range of activation with relatively constant force. Which, as I told you before, because with these A-night tie wires, because of its properties, you can tell that the curve of activation, the stress strain curve, is almost flat at different level of activation. So it delivers more or less the same level of force when the wire bend at different degrees. On the other hand, the M-night tie still remains useful, especially in the later stages. So the author is trying to tell you that it's better if you want to do a lining or leveling and use coil spring, it's better to fabricate and use wires that are made of A-night tie. And if you want to do finishing at the later stages, you still can use the M-night tie wires. And he's preferring or recommending using small round nickel titanium wires when you use the A-night tie. The rectangular A-night tie, some people still use rectangular A-night tie, but he's saying that the A-night tie is not enough, doesn't have enough torsional stiffness to induce any kind of torque. So maybe if you want to use rectangular wires, maybe you should use them large rectangular wire, maybe you should use them in other materials like the M-night tie or TMA wires or stainless steel wires. There's another type of wire, which is the beta titanium wire. So after nitinol was introduced, the regular M-night tie, and before the introduction of A-night tie, a new wire made of different titanium alloy, which is beta titanium, was introduced into orthodontics. And this beta titanium material was developed primarily for orthodontic use, unlike the nickel titanium wires. So this wire is somewhat between stainless steel wire and nitinol wire, has a desirable combination of strength and springiness, means it has excellent resilience as well as reasonably good for mobility. So maybe this is a good choice for auxiliary springs if you want to do like canine extrusion spring or intrusion arches, and also can be used for intermediate and for finishing using this wire as finishing wires, especially if you want to use large rectangular wires at the last stages or late stages of finishing, where sometimes it's difficult for us to fit rectangular stainless steel wire because stiffer wire. This can give you some resiliency. And by the way, I forgot to mention that strength, when you define strength is equal to range and stiffness. Range times stiffness equal to strength. The three wires are compared. The stainless steel wire, versus beta titanium and M or martensitic niti. You can see the orange or red color is the stainless steel, the gray one is beta titanium, and the green one is the M niti. You can see these are the three important features that if you want to compare wires, you should compare them to each other, like stiffness, strength, and range. See the range, the stiffness, we start by strength, strength of the stainless steel is almost double that of the beta titanium and niti, not really double, maybe less than that. And the stiffness highest for stainless steel, and then TMA has higher stiffness than the niti, and then range, the highest range was for the niti, the M niti was then more for the beta titanium, and the least was for stainless steel. And I forgot to mention in the previous slide also we have plastic wires that were introduced also to the market, and it took a while for them to prove their use in clinical practice, because they were not good to tolerate intraoral environment at the beginning, but later they were improved, and I expect in the near future we'll have a new improved wires, plastic wires. So when you compare wires, it's better to use the ratio of these features or properties that I mentioned before, the stiffness, the strength, and range. So when you say strength when you compare two wires, strength A over strength B, it will give you the strength ratio, stiffness ratio, and the range ratio. And by the way, just these ratios are used mainly for those wires that have or can follow the Hooke's law, which defines the linear elastic behavior of materials. Let me turn on the laser pointer here. So these are the ratios that I mentioned. Ratios were calculated by the late Robert Causey, and the data were taken from his work. This is what's written in Proffit's book. And when we compare properties of wires, we should consider two important points. First, that bending describes round wires reasonably completely in orthodontic application. However, for stainless steel or for rectangular wires, we need to evaluate bending and torsional stresses, not only bending. And because you know the application of torque using rectangular wire. But when we apply these ratios, the ratios can be used, or the equations can be used for torsion as well as bending in the same way. Important point that the ratios here apply to the linear portion of the load deflection curve. So it can be used accurately to describe the behavior of wires that have linear relationship in the stress strain curve, like the stainless steel wire, beta titanium, as well as the M niti. The A niti, however, it has abnormal or non-linear curve, so we cannot apply the Hooke's law on it. It's impossible to describe its features using these ratios. The efficient way to compare the properties of the wires is to use bar charts that show the three important properties: strength, stiffness, and range of the three important wires, stainless steel, M niti, and beta titanium, and compare them relative to a common reference, which is the 12 mil stainless steel wire. And because we compare all the wire types and sizes to the same reference, wires of different materials as well as different sizes can be compared. And this is an advantage of using these types of bar chart and compare them to one reference line. The bar charts that describe the bending strength, range, and stiffness of the three different types of wire, the three types of wire, the stainless steel, beta titanium, and the M-Nite. And you can see here the comparison of the three wires with different dimensions: strength, range, and stiffness. Here compare the torsional strength, range, and stiffness of the three wires at different diameters. As you can see, it's as the example explained in the book, comparing. Let's open this laser pointer first. If you compare the 21 by 25 mil wires, stainless steel, the red one, then beta titanium, and the green one is the M-Nite. If you compare, you can see that the M-Nite with the beta titanium around 4, the torsion strength of it when compared to all the wires are compared to the standard, which takes number one, which is the 12 ml stainless steel wire. So the torsional strength of the beta titanium is 4, and that of beta titanium of the M-Nite is around 6. So this means when you compare the two, you can tell that the M-Nite will be having a less chance of being permanently deformed when you twist it in the brackets, when you use it to torque a bracket, a wire. So the strength of it is higher than the beta titanium. And when you compare the stiffness of the same wire, the beta titanium and the M-Nite, the M-Nite is 3 and the beta titanium is almost double, 6. So this means this is the torsional stiffness. So this means that beta titanium will be delivering almost double the force when get twisted in the bracket. So this shows that the beta titanium is better option for you to deliver torque than the M-Nite. Properties that we described earlier of any wire, the stiffness, strength, and range, could be greatly affected by changing geometry of the wire, whether the size or the shape, round versus square versus rectangular, or 12 ml, 14, 16, 22, and higher size of wire, the diameter. And also they are greatly affected by the length of the wire between the two, like in the model of supported beams from each side or cantilever spring. But we have to keep in mind that these changes in size and shape are independent of the material. In other words, that decreasing the diameter of stainless steel wire by 50% would reduce strength to a specific percentage. If you do the same thing in TMA wire, same thing happens. The same percentage of reduction will happen. Either you do it in TMA or the stainless steel. However, the exact reduction percentage, this percentage, although it's similar between the two, but will depend greatly on how the beam was supported. Is it supported on each side or is cantilever spring model? And the performance of the beam between the two teeth in orthodontic appliance is determined not only by the geometry, also it depends on the material itself properties. So the three important factors that determine the property or the effect, or sorry, the behavior of the wires regarding stiffness, strength, and range are the diameter of the wire, the length of the wire between the two ends, and the material itself, the properties of the material, the nature of the material itself, and also finally the way the wire is supported in the model used. Here there are the two examples that we mentioned, the finger spring or the cantilever supported from one side only, or the other example of the beam supported from both sides, like the wire between two brackets. An example for the cantilever spring or the beam supported from one side is the finger spring that we use in removable appliance when we try to move a tooth out of crossbite or try to tip the tooth or the first molar distally. And another example is the cantilever spring used sometimes to extrude canine or intrude canine, as you will see it in the next part of this chapter. So increasing or doubling the diameter here, you can see how it greatly affects the wire, whether if it's supported on one side as finger spring or supported beam from both sides. So let's look at the first example. Doubling the diameter of cantilever spring. I forgot to turn on the laser pointer, but this is the finger spring model, supported beam on one side, and this is the supported beam from both sides. Example for this, like the wire between two brackets, and this is example for this is the finger spring, as I said, or extrusion or intrusion or canine springs. And as you can see, it's written here that doubling the diameter from D to 2D in cantilever or the beam type A will increase the strength 8 times and the stiffness 16 times and reduce the range by half. This is when you increase the diameter. So it's going to have stiffer wire, stronger wire, but less range wire. When you do the same thing with, if you look at these ratios, when you have supported beam from both sides, doubling the diameter will increase the strength by cubic function of the ratio of the two cross sections, 2D over D, and the springiness will change as the fourth power of the ratio, and the range will be directly proportional as change. We'll have, so you can see the range changes as a direct proportion. So you can see that although the trend is similar, that the strength and stiffness will increase, greatly affected, the range will be affected. Here will be cut into half, and here will be proportional. Supported beams, the situation a little bit more complex because it's more supported, so we expect it to be the beam to be stronger and less flexible, particularly if the ends are tightly anchored as opposed to being free to slide. So in a rectangular beam, when it's a rectangular wire, not round wire, its dimension is in the direction of bending. The dimension in the direction of bending is the primary determinant of its properties, not the other dimension. So, but the principle is the same. Same as the cantilever, and as I described before, the beam size increases. If the beam size increases, strength increases as cubic function, whereas stiffness increases as fourth power function, and range decreases proportionately and not exponentially. A direct relationship. Linear relationship. Proportionately means linear relationship. Torsion. Round wires really are not important in measuring torsion, but the more important is the rectangular wire, which has application when we twist the wire to apply torque. So we use rectangular wires and we never use round wires. In torsion, the analytic approach is similar to that in bending. However, the equations are a little bit different, and we use we measure shear strength, shear stress or strength rather than bending stress, and also the overall effect is the same. Like logic, if you decrease the size of a wire, it will decrease its strength and stiffness in torsion while increasing its range, just as in bending. If the wire decreases, it was found that its strength decreases so rapidly to a point that it's no longer adequate for orthodontic purposes. So you cannot use very small rectangular wire or very large. The same thing applies if you increase the diameter. It will reach to a point, make it too stiff to be used and to be fitted in the rectangular in the brackets itself. That's why the useful sizes vary from one type of material to another. Here shows you the useful sizes of the different materials. For the gold, we need larger size wires to be useful. For stainless steel, this is the standard. We can go from 12 to 20 or even larger, depends on the use. For example, sometimes you can use it for headgear or auxiliary expansion arches. Cobalt chromium is similar to stainless steel. Beta titanium is somewhat between these stainless steel wires and the nitile wires. You can see the nitile wires, the useful sizes are also should be similar to the rectangular wires, but they have more range and less strength than stainless steel wires. And but if you want to use the same you want to express the same strength and stiffness, maybe you should go to a higher sizes similar to the one used in gold. But in general, the nitile wires are springier and they have less strength than stainless steel wire. The length of the beam also affects the three important properties of the wire: the stiffness, strength, and the range. And also the way the wire is attached to in the model, whether it's cantilever or loosely tied to two brackets or tightly tied to two brackets, adjacent brackets. So if we double the cantilever beam length, bending strength will be cut in half, stiffness will decrease 8 times, and the range increases 4 times. And the same thing mainly applied on in case of torsion. So length changes in torsion or increasing the length in torsion will reduce stiffness and will increase range. However, the torsional strength will not be affected by increasing the length. And here showing you in this diagram, let me just show the laser pointer. This is when you double the size, what happened that the strength will cut in half, stiffness will be decreased 8 times, and the range will be increased 4 times. And if you change the way of attachment, this is different than the cantilever and also different than if it's tightly tied. You can see the difference. Tying the brackets will increase the stiffness, will increase, the strength of the wire and also the stiffness of the wire and cut range in half. So maybe if you want more flexibility of the wire, you should tie it loose tie instead of tying it strongly between two wires. Here also this picture shows the change from cantilever to supported beam. Change from cantilever to supported beam and how it affects the three features. So it complicates mathematics a little bit. It's more or less the same picture, but as the beam length increases, there are proportional decreases in strength, exponential decrease in stiffness, and exponential increase in range. Exponential decrease or increase يعني تسارع في الانكريز والدecrease. Also, the way the wire is attached can affect properties. If it's tightly tied or or loosely tied. And you can see that it affects the results dramatically. So a supported beam, such as an arch wire, is 4 times less stiff if it can slide over the abutment, يعني loosely tied, than if it's firmly attached tightly. With multiple attachments, the tie can affect the springiness, but less dramatic. Still significant, but in less dramatic way. But we should consider it when we tie wires if we want to have more strength or less stiffness, and less strength and more range, so we can control our or the desired property of the wire at that position by changing or modifying. So modifying the length, modifying the cross section, as well as the point or the method of attachment of or tying the wire into the brackets. Here what the author is trying to say is that we should balance strength, stiffness, and range in order to design that can achieve our objective, which is to obtain light but sustained force. So, for example, if you choose a very strong wire, maybe it's good to resist permanent deformation, but it will be too stiff in a way that it might create a force at the beginning and later on will decay rapidly when tooth begins to move. Or if it's flexible, too much range, this might fail to provide a sustained force if it distorts from inadequate strength at the beginning. So to balance strength, stiffness, and range, we have to know how to combine or balance between also the beam materials, what material we want to use, what diameter, and what length. For example, if you want to design a finger spring that we use in removable appliance, maybe you have to use a relatively large wire, selected wire, and a large wire with a larger diameter selected for its strength, and then we can increase its size to increase springiness to make it springy wire. So you can design your wire the way you want. And also we mentioned before that we want to do aligning or leveling. Maybe we should use 19-hole wires. Try to not tightly or firmly attach or tie the wire into the brackets if we don't need that much strength. And if we need to have also, this might affect the way we tie the wire on the brackets, also affect friction. So we have to balance all these things when we design or use our wire in the fixed appliance. The finger spring, as you can see in the picture here, doubling the wire occurs or can be obtained by doubling by making the wire more recurved or increasing its length and increasing or adding helices to it. You can add helices to it and making it more flexible. And by the way, the helix here is, I think it's misplaced, supposed to be directed to this way, not this way, to the front, not to the back. So there's mistake in the designing this finger spring. The helix supposed to be facing toward the mesial, forward, not backward, because usually how do you design it? You have to make the helix directing in a direction opposite to the direction of the movement. Since you're going to move this way, the helix was supposed to be designed the other way forward. So the same thing can be obtained when we use fixed orthodontic appliance. Here in the edgewise appliance, when we used to do using edgewise and where there was no night-tie wires, to align and level at the beginning, the initial stages, stainless steel small diameter wires were used with multi loops, as you can see, to align, because adding the length will increase the springiness and the range of the wire, will reduce stiffness. And also sometimes, as in C picture C, sometimes these loops were useful also to do torquing movement, especially in class 2 division 2. And if you really want to change the class 2 division 2 into division 1, if you want to do functional appliance, for example, maybe you can use these wires and bend them inward in order to create two-point contact to flare the incisors outward. And now, thanks God, with the introduction of nickel titanium, especially the A niti, made our life much easier. The super elastic A nickel titanium were the best wires to use. So during aligning or leveling, usually we start by 14 or 16 mil wires for the initial stage of aligning and leveling. And no more we need these loops. So here there is another also way to obtain combination of stiffness and range was by combining more than one wire together, like using the double or twin wire appliance to use two wires made of 10 mil stainless steel wires in order to add more flexibility for the wire. And then new wires came out which were like which contained more wires inside, like the twist flex wires, which have smaller stainless steel wire that were twisted together, more than two wires, three or more. And they were designed in several ways with different materials and with different strands, diameter, and they had exceptional combination of strength and springiness, but nowadays have been um, displaced or have been changed for most application by niti wire. If you have this breakthrough wire, the niti wire, why should you go and use the twist flex wire or stainless steel with multi loops? So nowadays, for initial aligning or leveling, is the best wire to use is the A niti wire. It gives you much easier aligning and leveling, and will give you continuous light force. Team A wire is not good for initial aligning or leveling. As we said, it's somewhere between niti and stainless steel, but maybe it's useful in the later stages of treatment, during the finishing stages and during space closure, if you use the looped arch wire. And also you can use it as springs because it gives you long low deflection curve. Give you it keeps the spring active for a longer period of time than stainless steel wire. Clear aligner materials. The clear aligner is made of plastic materials different than arch wires. Even the geometry is different, and there are a variety of thermoplastic polymers that are used to manufacture clear aligner, such as the polyethylene, polypropylene, and polyurethane that are used mainly. Polyurethane is one of the most commonly used in manufacturing clear aligner. These materials generally are 0.5 or 0.4 millimeter in thickness before being thermoformed into the aligner that you know about. And after that, of course, they will be thinned, and thinning it may affect the force delivery characteristic of the aligner, and it provides or apply lighter force than any wire. So if they designed or they draw a load deflection curve for these aligners. You can see here three different types of aligners here, and you can see that they have a force deflection curve, but definitely it's different than the wires in general. So here also, those materials, they have elastic modulus, and you can measure it, determined from the slope of the curve. However, the modulus values are not directly comparable to the arch wires. Why? Because aligners, as I said, they are different geometrically than wire. But it's clear from these graphs, if they're correct, that plastic materials or aligners can store enough elastic energy to create tooth movement. However, one of its main disadvantage is the stress relaxation of the aligner. Yani after some time, the aligner relaxes, undergoes fatigue, and loses the elasticity to apply force. You can see this is maybe the unloading and this is the loading curve. And there is a major difference between these aligners and night-eye wires is that the elastic range of aligner is much less than that of night-eye wire. So if we say that the effective force delivering range of night-eye is around several millimeters, then and for the aligner is limited to 0.2, then you can tell why to do just to displace or move a tooth 3 millimeter uh, into its ideal position requires many aligners, not only one wire. We can move displaced 3 millimeter displaced tooth from its ideal position by single night-eye wire, and we expect it to move, and also that it can create the necessary space that we need for that. However, to do that with aligners, you need maybe 5 or 6, and then you need another pair of another number of aligners also to create space. So maybe you need to do 20 individual trays to do such movement, which can be done only with night-eye wire. In addition, one of the disadvantages of the clear aligner is that the plastic are subject to stress relaxation and water absorption that may affect their ability to deliver tooth movement forces over time. That's why Align Corporation, which is the company that created Invisalign, has developed a material that they claim that it demonstrated less stress relaxation and relatively constant force delivery over 14 days period. And I suspect this information because uh, there are other reports that says that the decay or stress relaxation occurs in much less time than 14 days. And even the company now, they advise people to use those aligners only for 1 week, not 2 weeks. For rubbers and elastomeric materials, rubber from the beginning, rubber bands were used in orthodontics to transmit force from upper arch to the lower, like the class 2 elastic. Rubber has particularly valuable quality of great elastic range, so the extreme stretching produced when a patient opens the mouth while wearing rubber dam can be tolerated without destroying the appliance. Rubber bands are also easier for patients to remove and place than for instant or heavy coil springs, so they were convenient to be used. Important problem of the rubber is that it absorbs water and deteriorates under intraoral condition, especially the gum rubber that is used to make the households and offices was found also deteriorate in mouth within a couple of hours, and sometimes it loses elasticity in 12 to 24 hours. That's why people change to use the latex rubber instead of latex elastics instead of the gum rubber, and was 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 even 4 to 6 times uh, longer performance life than the gum rubber. Elastomeric plastics that are used for orthodontic purposes include the elastic power chain, the O-rings, the ties that we use them, elastomeric ties that we use them, or elastomeric modules on the brackets to tie wires, and also can be used for as inter-arch elastics. Unfortunately, like rubber, although it's stronger than rubbers in losing elasticity, these elastomerics deteriorate after a relatively short period of time. But this doesn't mean that they're not good. We still use them, and it's not contraindicated to use them to close small spaces and to use them as elastic to correct class 2. But we should characterize this the force that is delivered by these elastics as interrupted rather than continuous, because they lose their elasticity in a shorter period of time. And what the author is recommending here is, in order to ensure light continuous force, maybe you should use the A-NITI springs, the springs that we have in the market. They are more appropriate to deliver light continuous force. Earth magnets that were developed in 1980s were used also promoted for orthodontic force delivery. Why? Because they were able to generate forces by their traction and repulsion, and they claimed that they would have a biological effect that would speed tooth movement and reduce pain. These biological effects were found not true. That's why people stopped or reduced their interest in these materials, in these magnets. And by this we conclude the first part of the chapter, chapter 9, I believe. And I just want to clarify something, that I reviewed here the chapter as it is written. I delivered all the ideas of the author of the book. Thank you very much.